Hello everyone, and welcome to the first of the video lecture series for Introduction to Algebra. Um, this is Professor Hunter, and a couple of quick things before we get started is that all of these videos, since they are public videos, comments have been disabled. So if you have a question about anything on these videos, please feel free to email me with the video in question, and a timestamp would also be helpful. So the PowerPoint that goes with this video, along with the completed note outline and the blank note outline, are all posted on Canvas under the Unit 4 module. This is section 6.6, and this is the section that Unit 4 will get started with. Now, please feel free, if you want to print out the 6.6 note outline, the blank one, and follow along and take notes as you normally would in class. However, I have, for your convenience, also posted the completed note outline for 6.6, which contains all of the examples completely filled in and all of the blanks filled in. Also, feel free to follow along on your own PowerPoints if you wish to. If at any point you want to work on a problem before I go work through it, please feel free to pause the video and resume it when you are finished. However, for this video, I will just be going through each example. I also apologize in advance if my subtitles do not always match what I am saying. They are auto-generated. And I also apologize in advance if the stylus that I am using does glitch out and do weird things. I'm very sorry about that. There's nothing I can really do to fix it. So this section is going to be all about what's called ratios and proportions. So first of all, what is a ratio? A ratio happens when we compare two quantities, and ratios, we encounter these all the time. For example, win-loss ratios is a ratio between the number of wins and the number of losses. Recipes and really anything to do with baking and a lot of cooking does require a ratio. For example, 2 cups of flour makes 12 servings of a cookie. And price to earnings, it can be represented as a ratio. There are a lot of things in life that can be represented as ratios. Now, ratios can really be written in 3 different ways. So, for example, you can write the ratio 3 to 10 with the actual word 2, or you can use the colon notation 3 to 10. You might have seen this before. However, we are going to shy away from that, and we are going to favor this method of writing a ratio, which is writing a ratio as a fraction. So we are going to be writing all ratios in this course as fractions. So the formal definition of a ratio is a comparison of 2 quantities represented as a quotient or fraction. So you can have a ratio that's an improper fraction, and you're going to leave it like that. Do not turn it into a decimal. Do not turn it into a mixed number. When a ratio is improper, that means that the quantity on the top is just greater than the quantity on the bottom. So if you do have a ratio that's an improper fraction, do not turn it into a decimal. So most quantities in real life do have units, and if you have a ratio where the quantity in the numerator and the quantity in the denominator have the same units, they are called like quantities. So in a ratio of like quantities, the units can cancel out. Now, if you are comparing two unlike quantities is a comparison of 2 quantities that have different units or 2 completely different types of measurement. A rate is a ratio of unlike quantities, and we encounter rates every single day, all the time. For example, speed in a car is measured in miles per hour. So if you're driving at 30 miles per hour, that means that you are traveling 30 miles per 1 hour. So that is a ratio of unlike quantities, also known as a rate. Rate of pay is also a ratio of unlike quantities, $10 per 1 hour. Miles per gallon is another one. So these are all examples of rates, and we're going to be encountering a lot more rates in this section. So in order to simplify either a ratio or a rate, what you're going to do is you're going to represent that as a fraction, so write it as a fraction. I will say that if the ratio or rate involves money, money should always go in the numerator. If the ratio or rate involves time, time should always go in the denominator. Then you are going to reduce the fraction. And if the quantities are like, you're going to cancel out the units or drop the units. If the quantities are unlike and the units are different, you're going to keep the units. So for example, let's say that you travel 350 miles to 18 gallons of gas. We are going to represent that as a rate, and we are going to simplify it. So the first thing that I am going to do is I am going to represent, this is what I mean by my stylus glitches out. I don't know why it does that. So we are going to represent this as a fraction. 350 miles will go in the numerator, and then 18 gallons is going to go in the denominator. Now, since miles and gallons are two different units, they are unlike quantities, I'm going to keep the units. But if you notice, both 350 and 18, they are both even numbers, so I'm going to just divide both the top and the bottom by 2, giving us 175 miles to 9 gallons. So then for part B, hold on, give me one moment. I don't know why the subtitles stopped. Okay, so for the next one, there are 18 trees needed to produce 2,000 pounds of paper. I don't know why the subtitles keep cutting out. Hopefully it will listen to me eventually. So we're going to represent this as a ratio. So we're going to put the 18 trees in the numerator, and we are going to put the 2,000 pounds in the denominator. Then we are going to simplify this. 18 and 2,000 are both even numbers, so we're going to divide them both by 2. So 18 divided by 2 is 9 trees per 1,000 pounds of paper. And since the units are not the same, we are going to keep the units. All right, hopefully the subtitles will be working now. This is getting very annoying. But I am doing the best that I can with the limited technology that I have at my disposal. So just be patient. All right, so another type of rate that we have is what is called a unit rate. And a unit rate is a rate in which the denominator is 1. So, for example, let's say that you're on a road trip and you travel 130 miles in 2 hours, and you want to know your average speed, how far you travel per 1 hour. That requires you to find a unit rate. So a unit rate is a rate in which the number in the denominator is equal to 1. Give me one moment. I'm going to pause the recording to figure out what's going on with the subtitles. Okay, let's try that again. So what we're going to do for each of these is we are going to write them as unit rates. So for this first one, let's assume that on a trip that you traveled 275 miles in 5 hours, and you want to know your average speed in miles per hour. So what we're going to do is we're going to first represent this as a ratio, 275 miles per 5 hours. Then all you have to do to find a unit rate is take the numerator and divide it by the denominator. So on a calculator, you're just going to do 275 divided by 5, and you get 55. That is all you have to do. So what this will be as a unit rate is you travel 55 miles per 1 hour, or 55 miles per hour. That's all you have to do to find a unit rate. Express the quantities as a rate, and then take whatever's in the numerator and divide it by whatever is in the denominator. Now for this next one, let's say that you are paid $3,453 for 6 weeks. We're going to first represent this as a rate. Money should really always go in the numerator, and time really should always go in the denominator. So we're going to put the money in the numerator, and we're going to put the 6 weeks in the denominator. Then all you have to do is take 3,453 and divide it by 6, and you get 575.5. Remember, this is money, so you really should always go to 2 decimal places for money because this is cents. So this is $575.50 per week. So you get paid $575.50 per 1 week. So let's say to reduce expenses that a commuter buys a fuel-efficient car, and if the car is able to travel 60 miles on 2.5 gallons of gas, we're going to find its fuel economy, or its miles per gallon. So this is how you personally can also figure out miles per gallon on your own. You can always take the number of miles that it takes to travel on a tank of gas and then divide it by the number of gallons that it took to fill your tank again, and that will give you your average fuel economy or your average miles per gallon. So what we're going to do is we are going to put the 60 miles in the numerator, and then we're going to put the 2.5 gallons in the denominator. This is really the only amount of work to show here, because all you have to do to find the unit rate is take 60 and divide it by 2.5, and you get 24. So your fuel economy is 24 miles per gallon, or 24 mpg. mpg is completely acceptable. So 24 miles per 1 gallon of gas. Now, there are a ton of different unit rates out there, such as miles per gallon, miles per hour, dollars per hour, but there are specific unit rates that are called unit prices, and these specifically deal with money. So if you're comparing the prices of items, it is often helpful to look at the unit price. So some stores do have the unit prices labeled right on the shelf barcode. However, if they don't, it is really easy to actually compute unit prices to figure out which of these is the best bargain. So the unit price is a unit rate involving prices of things. So a unit price is the price of one item or one unit. So one unit could be, for example, ounces, or one item. So it really depends on the item that's being sold. So let's say that, a gym, for example, offers costs $300 for 12 months of membership, and we're going to find the unit price for this. Now, for unit price, money always goes in the numerator. So I'm going to put the $300 in the numerator, and I'm going to put the 12 months in the denominator. Then, just like with any other unit rate, all you have to do is take whatever's in the numerator and divide it by whatever's in the denominator. So 300 divided by 12 is equal to 25. So what this means in context is that this gym costs $25 per 1 month. So then for Part B, a 6-credit course is offered for $234. So what we are going to do is we are going to take this and represent it as a ratio. So we're going to put the money in the numerator. We're going to put the $234 in the numerator, and we're going to put the 6 credits in the denominator. Then you take the 234 divided by 6, and you get 39. So what this means in context is that this costs $39 per 1 credit. Then for Part C, a 10-ounce box of wheat flakes costs $2.70. So what we're going to do is we're going to put the money in the numerator. So we're going to represent this as a ratio with $2.70 in the numerator and 10 ounces in the denominator. Now, instead of, individual items, this is going to be measured in ounces. So our unit price is going to be price per ounce. So if you do 2.70 divided by 10, you get 0.27. So what this means in context is that this costs 27 cents per ounce. So this cereal costs 27 cents per ounce. So finding unit prices can be really handy when you are comparing two different size boxes or two different brands of the same thing, and you want to figure out which is the better bargain. So what we're going to do for each of these is we are going to find the unit prices for each of these boxes, and whichever one has the lower unit price will be the better bargain, because we will be paying less per individual unit. So we're going to start with the small box. So in the small box, there are 30 bandages in here, and it costs $3.18. So we're going to represent this as a ratio. I'm going to put the money, $3.18, in the numerator, and I'm going to put the Band-Aids, 30, in the denominator. Then I'm going to take 3.18 and divide it by 30. Now remember, this is money, so we should always round to 2 decimal places. So if you round appropriately to 2 decimal places, you get 11 cents per Band-Aid. So that means in this small box, each Band-Aid costs 11 cents. Now let's do the big box. So for the big box, we're going to represent this as a ratio. We have 100 Band-Aids, and the box itself costs $9.49. So I'm going to put the money in the numerator, $9.49. And then I'm going to put the 100 Band-Aids in the denominator. And remember, you should always round to 2 decimal places whenever you are dealing with money. So if you do 9.49 divided by 100, rounded to 2 decimal places, you get 0.09. So what this means is that in this box, each Band-Aid costs 9 cents. So it costs 9 cents per Band-Aid. So because the big box has the lower unit price, the big box is the better buy. Because you are paying, in the end, you are paying less per Band-Aid if you buy this bigger box. Now, the next part of this section is going to deal with what is called proportions. And a proportion is a statement that 2 ratios are equal. So these here, down at the bottom of the slide, are 2. Let's give it a second. Let's let it do its thing. Give me one moment. Okay, there we go. So a proportion is a statement that 2 ratios are equal. So each of these down at the bottom of the slide are examples of proportions. 1/2 equals 4/8 is a proportion. So some proportions are going to be true, some proportions are going to be false. One way to see if a proportion is true is to determine whether the cross products of those ratios are equal. And what cross products involve is also a process called cross multiplying, is taking the numerator of one of the fractions and multiplying it by the denominator of the other. That is how you test to see if a proportion is true. So I know you guys know that 1/2 does equal 4/8, but I'm going to show you how you can use cross products to figure out if this proportion is actually true. So I'm going to take the numerator of one fraction and multiply it by the denominator of the other. And it really doesn't matter which one you start with. I'm just going to start with this one. It doesn't really matter if you started with the other one or not. So I'm going to take the numerator 1, multiply it by that denominator 8. And I'm going to see if that equals the other cross product. So I'm going to take the numerator of the other fraction and multiply it by the denominator of the first fraction. So I have 2 times 4. All right, 1 times 8 is 8. 2 times 4 is 8. 8 does indeed equal 8, so this proportion is true. So I'm going to do the same thing for this next one. We're going to see if 5/3 equals 16 over 12. So I'm going to take the numerator of the first fraction and multiply it by the denominator of the other fraction. So I'm going to take 5, multiply it by 12, and we're going to see if that equals the other cross product. So I'm going to take the numerator of the second fraction, 16, multiply it by the denominator of the first fraction, 3. 16 times 3 is 48. So 5 times 12 is 60. 60 does not equal 48. So this proportion is not true. This proportion is false. Now you might be wondering, when in the world would you ever do something like that? Why would you ever do something like that? And what is that really used for? So let's say that a college claims that its student to faculty ratio is 13:1. So what a claim like that would mean is that on average, there are 13 students per 1 faculty member. In general, the lower the student to faculty ratio, the better. Now let's say that the actual enrollments of the college look like this. Let's say that at this college there are actually 96 faculty and 1,248 students. So what we're going to do is we're going to set up a proportion to see if the college's claim is actually true. So let's start with the college's claim. I'm going to set up this 13:1 as a ratio. Now the 13 stands for students and the 1 stands for faculty. And it really doesn't matter how you set up the first ratio, just keep in mind the format that you did set it up in. So the first ratio is going to go like this: 13 students to 1 faculty. Now, you have to keep in mind how you set up that first ratio, because in order for this proportion to even work, or have a possibility of being true, the other ratio needs to be set up in the exact same way. So in the other ratio, since students was in the numerator of the first ratio, students needs to go in the numerator of the second ratio. And since faculty was in the denominator of the first ratio, faculty needs to go in the denominator of the second ratio. So for this 96 faculty to 1,248 students, I'm going to put the number of students in the numerator, 1,248 students. Then I'm going to put the 96 faculty in the denominator. So the numerator of each fraction contains students. The denominator of each fraction contains faculty. So these two ratios are set up in the exact same way. You need to make sure of this. So then what we're going to do is we are going to cross multiply. We're going to do 13 times 96, and so we're going to do 13 times 96, and we're going to see if that equals 1 times 1,248. So does that equal 1 times 1,248? Well, 13 times 96 is 1,248. And then this also equals 1,248. So since we got the same number on each side of the equal sign, is the college's claim true? Yes, the college's claim is true. The proportion that we set up, the cross products are actually equal. Now that same cross-multiplying process is also used for solving proportions, which involves the one part of the proportion being unknown. So what we're going to do is a lot of proportions are going to be solved in word problems, so we're going to do a bunch of proportions that are not in any sort of context, and then we're going to actually put them in a word problem as an application to see how this would apply to the real world. So to solve a proportion, you're going to set up a proportion based on the given information, and the variable is going to be used to represent the unknown quantity. Then you're going to cross multiply or find the cross products and set them equal to each other. That will give you some sort of equation that you can then solve using the methods that you have learned to solve equations, and in the end you will be dividing both sides by something. Now, remember, in order to set up a proportions, you need to put the quantities of the same kind in each of the numerators and the quantities of the same kind in the denominators, just like with the student-faculty ratios. The ratios need to be set up the exact same way in order to successfully solve the proportion. So this is an example of a proportion. The numerator of the second fraction is unknown, and we are going to solve for it. So what we're going to do is we are going to cross multiply. So it doesn't really matter what order you start in. It doesn't matter. So we're going to do 3 times x, which is 3x, equals 2 times 15, which is 30. So this gave us a one-step equation that we can then solve. We're going to divide both sides by 3. And we get x equals 10. So some proportions are really simple like this, and other proportions are going to be slightly more complicated. So this is another example of a proportion where the numerator of the second fraction is unknown, so we are going to cross multiply. So I'm going to take 2, multiply it by x, which gives us 2x. Then I'm going to set that equal to the other cross product. 5 times 4 is 20. Then I'm going to finish solving for x by dividing both sides by 2, and that gives us x equals 10 for our final answer. Now for something like this, whenever your fraction, either in numerator or denominator, contains addition or subtraction, please put parentheses around it. You have to put parentheses around this because the entire denominator is going to be multiplied. So yes, this is going to involve distribution. You are going to have to distribute. That is why you need the parentheses. So first, let's cross multiply. So we're going to take 8, and we're going to multiply it by x, gives us 8x. And we're going to set that equal, parentheses, x plus 3 times 4 is 4 times parentheses x plus 3. Then, if you remember from chapter 3, in order to clear out parentheses, you are going to distribute. So we're going to distribute the 4 to clear out this parentheses. So 4 times x is 4x, and then 4 times 3 is plus 12. Then if you take a look at this, there are variable terms on both sides of the equal sign. So all of the variable terms do need to be moved all onto one side. So I'm going to move this 4x over to the other side by subtracting it from both sides. So 8x minus 4x is 4x. Leave the equal sign where it is, 12. Then we're going to finish this up by dividing both sides by 4. And then for a final answer, you get x equals 3. So anytime that one part of your fraction contains addition or subtraction, you do need to put parentheses around it before you cross multiply. This is another example of that. The denominator of the first fraction contains addition, so I'm going to put parentheses around it before I do anything. And then this denominator over here also contains subtraction, so I'm going to put parentheses around it as well. So, keeping in mind that there are parentheses here, we are going to cross multiply. So I'm going to take this 6 and I'm going to multiply it by parentheses 5x minus 13, gives us 6 times parentheses 5x minus 13. Then I'm going to set that equal to the other cross product, so I'm going to take 12 and multiply it by parentheses x plus 4. Then, to clear out the parentheses, I'm going to distribute, so I'm going to do some distribution on the left and some distribution on the right. So over here, I'm going to take this 6 and I'm going to distribute it, so 6 times 5x is 30x. And then 6 times negative 13 is minus 78. Leave the equal sign where it is. And then on the right here, I'm going to distribute this 12. So 12 times x is 12x. And then 12 times 4 is plus 48. Then you might notice that there are variables on both sides of the equal sign. So all of the variable terms do need to be moved onto one side. So I'm going to move this 12x over to the other side by subtracting it from both sides. So I'm going to subtract 12x from both sides. So then 30x minus 12x, that will give us 18x, minus 78 equals 48. Now this is a two-step equation that we can now start to solve. So I'm going to get rid of this minus 78 by adding 78 to both sides. I'm going to continue over here in the top right. So if we're going to get 18x equals 48 plus 78 is 126. Then we're going to divide both sides by 18. And that gives us x equals 7 for our final answer. Now let's actually start applying that to some real life context. One context that you can apply this to is hourly pay. So let's suppose that you earn $840 working part-time for 4 weeks. At this rate of pay, we're going to figure out how much we will earn in 10 weeks. So the thing with proportions is you are given two ratios and one part of one of the ratios is going to be unknown. So you need to figure out what the variable x is going to stand for. How much will you earn in 10 weeks? So the variable x is going to represent how much money we will earn in 10 weeks. So x is going to represent this unknown amount of money. So with proportions, you are always given one complete ratio. The complete ratio that we are given is this $840 earned in 4 weeks. So I'm going to represent that as a ratio. I'm going to put the money in the numerator and the weeks in the denominator. So $840 is going to go in the numerator, and then the 4 weeks is going to go in the denominator. Then I'm going to set that equal to the other ratio. Now remember, if you put money in the numerator of the first ratio, money needs to go in the numerator of the second ratio. We put weeks in the denominator of the first ratio, so weeks needs to go in the denominator of the second ratio. So how much will you earn in 10 weeks? So I'm going to put the 10 weeks in the denominator, And since our variable is going to stand for money, I'm going to put it in the numerator since money went in both numerators and weeks went in both denominators. Now, when you cross multiply, you don't have to have the units there. You do need units on your final answer, but I put the units here just so that you could see that we have the same type of quantities in both of the numerators and both of the denominators. So when we cross multiply, I'm going to do 4, and I'm going to multiply it by x, gives us 4x. And then I'm going to set that equal to 840 times 10 is 8,400. Then to finish getting x by itself, I'm going to divide both sides by 4. And then yes, your final answer does need units. So x is going to equal 2,100. And since this was money, you get paid $2,100. This is another example of a context in which you could apply proportions. So let's say that 9 ceramic tiles are required to tile a 4 square foot area. At this rate, how many square feet can be tiled using 270 ceramic tiles? So let's figure out what the variable stands for and what the units on our final answer should be. How many square feet can be tiled with 270 tiles? So our x in this case is going to stand for this unknown number of square feet. So remember, in a proportion, you are always given one complete ratio, and then one part of the other ratio will be unknown. So the complete ratio that we are given is that 9 tiles are required to tile 4 square feet. So I'm going to represent that as a ratio. So I'm going to put the 9 tiles in the numerator, and I'm going to put the 4 square feet in the denominator. Now, you have some flexibility of how you set up that first ratio, but keep in mind, however you set up the first ratio, you need to set up the second ratio in the exact same way. So if tiles went in the numerator of the first ratio, tiles needs to go in the numerator of the second ratio. If square feet went in the denominator of the first ratio, square feet needs to go in the denominator of the second ratio. So how many square feet can be tiled using 270 tiles? So I'm going to put the 270 tiles in the numerator since both numerators should contain tiles. How many square feet? I'm going to put my unknown number of square feet x in the denominator since both of the denominators are going to contain square feet. So then what I'm going to do is I'm going to cross multiply. So I'm going to do 9 times x, which is 9x, equals 4 times 270 is 1,080. Then I'm going to finish getting x by itself by dividing both sides by 9. And remember, your final answer does need units, so x equals 120 square feet. So you could tile 120 square feet with 270 tiles. Voting is another application of proportions, so we're going to set up a proportion to solve this voting problem here. So let's say that an exit poll showed that 5 out of every 7 voters cast a ballot in favor of an amendment to the city's charter. At this rate, how many people voted in favor of the amendment if 21,000 people total voted? So this one is a little tricky because both numerators and denominators both involve voters. However, you have either voters in favor of the amendment and you have voters that, you have the total number of voters. So the first complete ratio that we are given is this part right here. 5 out of every 7 voters were in favor. So that means out of every 7 total voters, 5 of them were in favor. So I'm going to set that as a ratio. So we're going to have 5 voters in favor in the numerator out of 7 total voters in the denominator. Now just keep in mind, however you set up the first ratio, you need to set up the second ratio in the exact same way. So the number in favor went in the numerator of the first ratio, so I need to make sure that the number of people in favor goes in the numerator of the second. The total number of voters was in the denominator of the first ratio, so total number of voters needs to go in the denominator of the second ratio. So now let's figure out what our variable stands for. How many people voted in favor of the amendment if 21,000 people total voted? So X is going to stand for the unknown number of people total, the unknown number of people who voted in favor of the amendment. Now, this 21,000, there were a total of 21,000 people that voted, period. For, against, whatever. 21,000 people total voted. So I'm going to put that 21,000 in the denominator of the second ratio because this is the total number of voters, and total needs to go in the denominator of both ratios. X stands for the unknown number of people who voted in favor, so X is going to go in the numerator since people in favor were in both of the numerators. Now I'm going to cross multiply and start to solve for X. So we've got 7 times X, which is 7X, equals 5 times 21,000 is going to give us 105,000. Then I'm going to divide both sides by 7. Those cancel out, giving us X equals 15,000. So this means that 15,000 people voted in favor of this amendment. So 15,000 voted in favor. Now, maps or anything else that is drawn to scale also follows a proportion. So this could apply to scale models as well. Whenever something is drawn to scale, that means that the number of inches or centimeters that is in the model will stand for the number of feet or miles in real life. So in the context of maps, maps are drawn in such a way that the number of inches that is on a map will correspond to a certain number of miles in real life. So each map is different. In this particular map, it actually gives us a complete ratio right here in the map's key. That means that on this map, every half inch stands for 100 miles in real life. So if you measure half an inch on that map, that stands for 100 miles in real life. So if St. Louis and Cincinnati on this map are 1.6 inches apart, so you take a ruler, measure it, they are 1.6 inches apart. What is the actual distance in miles between them? So X is going to stand for the unknown number of miles between them. So for the first ratio that you are given, we are actually going to use the map's key. This 1/2 inches equals 100 miles. And just for the sake of ease, I'm going to change the 1/2 inches to a decimal. So let's set that up as a ratio. So I'm going to put that 0.5 inches in the numerator here, and I'm going to put the 100 miles in the denominator here. Now, it didn't matter if you switched them. In this case, you have a lot of flexibility, but however you set up the first ratio, you need to make sure that the second ratio is set up in the exact same way. So if you put inches in the numerator of the first ratio, inches needs to go in the numerator of the second ratio. These cities on the map were 1.6 inches apart, so I'm going to put the inches in the numerator of the second ratio. I put the real life distance miles in the denominator. What is the actual distance in miles between them? That means our unknown X is going to go in the denominator here. Now, it doesn't really matter where your X is, if it's on the top or on the bottom. The cross multiplying process is the exact same regardless. So I'm going to cross multiply. So 0.5 times X is 0.5X equals 100 times 1.6 is 160. Then we're going to divide both sides by 0.5 or multiply by 2, whichever. And you get X equals 320. And remember, you need units, miles. So that means in real life, these two cities are 320 miles apart. Now, if you ever took a geometry class in high school, you've probably solved problems like this. When your ratio contains quantities of the same unit, such as the voter example where you had people for both the top and the bottom, setting up your ratios can be really tricky. So in this case, everything here is in meters, but we have heights and we have shadows. So we just have to make sure that in the ratios that we set up, heights go in the same part of the ratios and shadows go in the other part of the ratios. So in this diagram, we have a person standing next to a tree, and we know the height of the person is 1.6, and we know that the person casts a shadow that is 2.4 meters long. And then he's standing next to a tree, and we know that the tree casts a shadow that is 10.8 meters long, and we are trying to find the height of the tree h. So h is going to be the unknown height of the tree. And we're going to set up a proportion to solve this. Now, the proportion that we're going to set up are ratios between the height of the person and the length of the person's shadow, and the height of the tree and the tree's shadow. So let's start with the person. The person gave us the only complete ratio that we have. So I'm going to set up a ratio between the person's height and the person's shadow. And it doesn't really matter how you do this. You just have to keep in mind that however you set up the first ratio, the second ratio needs to be set up the same way. So if I put the person's height in the numerator of the first ratio, I need to make sure that the tree's height goes in the numerator of the second ratio. So I'm going to put that 1.6 meters high in the numerator, and I'm going to put the shadow 2.4 in the denominator. Now I'm going to set up the heights for the numbers for the tree in the exact same way. So if the person's shadow went in the denominator, the tree's shadow needs to go in the denominator. So I'm going to put the tree's shadow in the denominator. And then the tree's height, which we don't know, is going to go in the numerator. So h, the unknown height of the tree, is going to go in the numerator because the person's height went in the numerator. So each of these ratios has height in the numerator and shadow in the denominator. Now what we're going to do is we are going to cross multiply to solve. And yeah, there's a lot of decimals here. A calculator is required for this course, so it shouldn't be a big deal. So cross multiplying this way, 2.4 times h is 2.4h equals 1.6 times 10.8 will give you 17.28. Then to finish getting h by itself, we're going to divide both sides by 2.4. And we get h equals 7.2, and this is going to be in meters. So what this means in context is that the tree is 7.2 meters tall. Alright, so that wraps up section 6.6, which is ratios and proportions. Now, the next section that we're going to be covering after this is section 3.2. I'm sorry that we're jumping around a lot, but section 3.2 actually uses proportions in another context, percents. So after this, we're going to be moving on to section 3.2. Make sure that you do the section 6.6 homework and fully read through all of the notes before you move on to section 3.2. If you have any questions, please feel free to email me, and I will see you all in the next video. Thank you all very much for watching. See you later.